This should be video physics. I'm writing it down. 28B Blake. And we are in the chapter review. And we just finished problem 51, I think, which was a bird on page 235. And now we are on number 55, page 237. And we have a 730 Newton student, stands in the middle of a frozen pond with a radius of 5 meters. Because there's no friction, he throws the 2.6 kilogram textbook horizontally towards the north shore, which will make him go to the south shore at a slower rate, assuming the book is much less mass. And the book goes at 5 meters per second. So how long does it take him to reach the south shore? If he's in the middle of the radius of 5 meters, he's got to go to 5 meters. So we need to know the mass of this student. So if you say F equals ma, force of gravity on this student, which is his weight, is 730 newtons, is equal to mass times gravity, 9.81 meters per second squared. The mass of the student comes out to be 74.4 kilograms. So together, the student and the book have a mass, or have a momentum of 0 kilograms times meters per second. And once they're thrown, that center of mass stays right there in the center of the pond, while the book goes that way and the student goes this way slowly. So the momentum of the student and the book are equal and opposite. One of these two is negative. It doesn't really matter which one you call negative. Go walk around the other side of the pond and look at it the other way. But if we call the book 5 meters per second positive, then when we then the student would be negative, and when we subtract it to the other side, it ends up positive. Well, maybe not. Nah, I'm not going to get into that right now. So the mass of the book is 2.6 kilograms. The speed is 5.0 meters per second, divided by 74.4 kilogram mass, and the velocity is 0.175 meters per second. And if you want to know how much time this takes, I think that asks that. Then you're going to slide at x equals vt at a constant rate by the time you cancel this out. We're going to go 5 meters at 0.175 meters per second times t. T is going to come out to be 29 seconds. Okay, then next is 57. I should have kept these on one video, just made it longer. Okay. Oh, this is ye old ballistic pendulum problem. I'm ordering, and all the stuff I'm going to order at the end of the year, a ballistic pendulum. It's only 60 bucks. I thought it would be hundreds. But we're going to shoot a projectile into a mass, and then it's going to have a momentum that we can predict, which gives us a speed that we can predict, which gives us a kinetic energy that we can predict, and then it swings up to a height that we can predict because of gravitational potential energy. This is number 57. I guess we got one more after this. So an 8-gram bullet's fired into a 2.5 kilogram pendulum bob becomes embedded. If the pendulum rises a vertical distance of 6 centimeters, calculate the initial speed of the bullet. Or, in this case, we can do the reverse. If we know this goes up a certain height, we know what's gravitational potential energy combined, which tells us it's kinetic energy right after the collision. If we know its kinetic energy right after its collision, we can find its velocity right after the collision. If we can find its velocity right after the collision, we can find its momentum right after the collision. And if we know the momentum of this, then we can find the momentum of that. Let's see how I did this. So I'm saying that the momentum of the pendulum is 2.5 kilograms, is 0 because velocity is 0. Bullet hits it, and we know this combined, or we can know this combined. We don't have either velocity. So first we have to find this velocity, and then we can figure it out. So combined, it's 2.508 kilograms. Let's find that velocity. We know how high it went. We know its gravitational potential energy. We can find its kinetic energy, velocity, and then momentum. Okay, so gravitational potential energy equals kinetic energy up here. mgh is equal to 1/2 mv squared. So for this particular calculation, we don't need the mass. It's 9.81 meters per second squared times 0.060 meters. It's 1/2 v squared. The velocity, when this went bang and collided and went up, the velocity right after that collision was 1.1 meters per second. Now that we know that this is 1.1 meters per second, we can substitute back in here, and this comes out to be 340 meters per second for the velocity of this bullet. And that is shown, oops, not on the next page. You can try that. 1.1 times 2.508 divided by 0.008 comes out to be 340 meters per second. So we need to get a ballistic pendulum to do this lab so you can see it, but that won't happen for you guys. But do the problem, you get the gist of it, you have some experience with it. Next problem I want to do is 59. And we do not have the piece of equipment, and I'm going to order this because this isn't very much either. It's a collision in 2D apparatus. And we need to study that. It turns out this year we wouldn't have had time with the pandemic anyway. There's a lot of labs, including force table, we've done up to this point just so I can do that lab. But you roll a ball down a little ramp, and it hits another ball, and they go out 2 directions. And you got to study the momentum this way colliding with the momentum that way. Which we've done that sort of thing, but we haven't done it while they were falling. So if you do that, you've got a nucleus with a mass of 17 times 10 to the minus 27 kilograms at rest, disintegrates. One of the particles moves along the positive y-axis. Here. With a speed of 6.06 meters per second. Actually, that speed is not this. That speed times the mass is one of those. I might have something wrong here. Okay, good, the problem is I just read wrong. Here's the positive y-axis. I'm going to move this if I can. It's not drawn very good. That's a little better. Okay, so you have 3 pieces. What is conserved, if this happened on a sheet of ice, what is conserved is the momentum in 2 dimensions. The momentum is conserved in all 3 dimensions, but you'll probably I've never worked a problem where it was in all 3 dimensions. It wouldn't be bad to just add another dimension. And instead of a squared plus b squared is equal to c squared, you'd have a squared plus b squared plus c squared equals to d squared. So everything would be more steps, so it'd be harder, but it's the same steps. All right, so momentum is conserved. So we know this momentum vector is 3 times 10 to the minus 20th kilograms times meters per second, because we have the mass times velocity. Then in the x direction, we have a particle that goes 4 million meters per second. 4 times 10 to the 6 meters per second. Times this mass of 8.4 times 10 to the minus 27th kilograms. So when particles decay, and you probably talked about this in physical science, radioactive decay, it's like, these particles are real tiny and they're moving real fast. 3 times 10 to the 8th meters per second is speed of light. So these are moving pretty fast. I mean, they're moving at this one's moving at over 1% of the speed of light, and this one is moving at 2% of the speed of light. So that's blistering fast. So what you're going to have is your nucleus, most of it is going to go, mass is going to go this way at a much lower speed, because it's going to be more massive than these ones going near the speed of light. And when I say 1 or 2% of the speed of light, that's, in relativity purposes, near the speed of light. Because it's really fast. Relativity comes into play. Okay, so with the x, you've got the momentum this way in the y, and the momentum this way in the x. So you got to multiply mass times velocity. There's 3.36 times 10 to the minus 20th kilograms times meters per second. So you got to go, to get this piece, you got to go out this far, the opposite of that one, and down this far, the opposite of this one. Working in momentum, because momentum is conserved. So all you've got to do is take negative 3 times 10 to the minus 20th down this way, and negative 3.36 times 10 to the minus 20th this way. I got a 0 missing here. And I'm going to square it, so I probably didn't write my zeros in there for that reason. It's not going to matter. Equals let me fix this. Yeah. And then take the square root of that. And you will get the momentum. And then you can change that to velocity if you need to. There. So the momentum resultant this way is a squared plus b squared equals c squared. You've done that. You know how to do it. And that comes out to be apparently 4.5 times 10 to the minus. And I'm not sure what I did here. I gotta see what the question is. Speed and direction of motion. Okay, so this is the momentum. So what I did, I have the mass of the whole, I need the mass of that particle. Here's the problem. I need the mass of this particle. I know what it was before it went splat. And I know what this is, and I know what this is. So to get the mass of this particle, I take all the mass minus that, minus that. And all the mass was 17 times 10 to the minus 27th kilograms. Minus the mass of one particle, minus the mass of the other particle. The piece that's going pew this way must have a mass of 3.6 times 10 to the minus 27th kilograms. So if I know this must be my momentum at this angle, and this must be my mass at this angle, then momentum is mass times velocity. I know these two. My velocity at that angle must be 1.25 times 10 to the 7th meters per second. Which actually, I thought this was going to be the heavy particle, but it must be the lightest particle because it's faster than these two pieces. I think this is a made-up problem. Because usually when you, okay, let's not worry about that, but usually when you blow up a nucleus, one particle is way lighter than the others, is moving way faster. And the nucleus itself is way heavier, moving way slower. So how do you get the angle? Well, you've got this momentum. As a matter of fact, you've got this momentum and this momentum and this momentum. So I'm not sure which way I did it. Probably if you take this one out here, I guess you could use this one over that one and get the angle. That'd be, if you move this one over here, you'd have the adjacent and the opposite, and you could work tangent and get that angle and then add it to 180. That's probably what I did. So I probably did this number and tangent. And that's what it looks like. Okay. I did opposite over adjacent, so I did 3.36 times 10 to the minus 20 divided by 4.5 times 10 to the minus 20 and came up with 41.7 degrees. Nope, I did cosine, which isn't really the smartest way to do this. I did adjacent over hypotenuse and I used this one because it has an extra step, so if I made a mistake, I would have. Okay, so 3.36 times 10 to the minus 20 divided by 4.5 times 10 to the minus 20 equals cosine theta. Theta comes out to be 41, and if you're going to add another 180 degrees on it to get that total amount of 222 degrees. So this is an example of conservation of momentum in two directions. We've already done this kind of math with forces and velocities. All we're doing is applying that very same skill set to conservation of momentum. Okay.